Welcome to Pythagorean Theorem Podcast. We're on a new section. This section is Pythagorean Theorem and trig ratios. So we're going to be using Pythagorean Theorem to find unknown measures. In the 1939 film The Wizard of Oz, after receiving a brain from the wizard, the scarecrow stated, "The sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side." On The Simpsons, Homer finds a pair of eyeglasses in a public restroom. Homer's recitation is the same as the scarecrow's, although Homer receives a response. Homer, the sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. Man in the bathroom stall. That's a right triangle, you idiot. Homer, don't. So who's correct? When can we use Pythagorean theorem? So is the scarecrow correct? Is Homer correct? Or is it the man in the bathroom stall? Well, the correct answer to that is it's the man in the bathroom stall. We can only use Pythagorean theorem for right triangles. And the only kind of isosceles triangles that we can use Pythagorean theorem with is if it's a right isosceles triangle. So this is for right triangles. So recall a right triangle is a triangle with a right angle. Right? And so the two sides that form the right angle are called the legs. And the opposite side, the side opposite the right angle, is the hypotenuse. It's also the largest side in the triangle. So when you're solving for the hypotenuse, it better be larger than the two legs, otherwise you definitely have made an error. Right? And this information is already filled in your notes for you. So Pythagorean theorem. Over 2,500 years ago, a Greek mathematician named Pythagoras developed a proof that the relationship between the hypotenuse and the legs is true for all right triangles. So in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. So in other words, when we square the legs and we add them up, we're going to get the exact same value for the hypotenuse, so long as it is a right triangle. It is believed that this theorem was known in some form long before the time of Pythagoras. 1,000 years before Pythagoras, the Babylonians recorded their knowledge of the theorem on clay tablets. And actually a lot of what the Babylonians knew of mathematics we're able to see today because those clay tablets are very, very sturdy. They were very smart to write them on clay tablets. The Egyptians used the concept of the theorem in the building of the pyramids. In 1100 BC China, Chao Gun knew of this theorem. It was, however, Pythagoras who generalized the theorem to all right triangles, and it is credited with its first geometrical demonstration. Consequently, the theorem bears his name. So there were other civilizations that knew of the theorem, but they couldn't show it was true all the time. They weren't able to prove it, but Pythagoras was. And that's why it's called Pythagorean theorem after him. So the area of the square described upon the hypotenuse of a right triangle is going to be equal to the sum of the areas of the squares described on the other two sides. So in other words, let's say, for instance, this side here is 6. Right? So if that side is 6, the area of that the area of that square is 36, right? Because it would be 6 squared. Let's say this is 8. Okay. Well, the area of that square would be 64. Well, guess what this area has to be? Well, this side here is going to have to be 10. And this area here of this square is 100. Right? And so Pythagoras was able to show that that's true all of the time for all of our right triangles, that those areas of those two squares that are formed by one side of a right triangle are going to be equal to the area of the square whose side is a hypotenuse. In your notes, you get the first thing to write in red here. Right? So here you have that diagram in your notes. Right? And so A and B here are the legs. C, so you're just going to fill in the red here. C is the hypotenuse. And C is always across from the right angle. And you have this in your notes. It's just not right above this square. It's kind of right below the it's not right above the triangle like it is in mine. It's a little bit below the triangle, but you do have that formula already in your notes for you. All right, so if we know the measures of two sides of a right triangle, we can find the measure of the third side using Pythagorean theorem. Before we get into Pythagorean theorem, I want to go over squaring radicals, because sometimes one of our side measures might be a radical. We'll have to square a radical. But it's really, really easy. So here I have two of them, and you're going to fill in the answers in your notes. So I have the square root of 6 squared. Well, the square root of 6 squared is the same as the square root of 6 times the square root of 6. And when we multiply radicals that have the same index, in other words, they're both square roots or cube roots or whatever, we multiply the radicands, what's under the radical sign. So the square root of 6 times the square root of 6 is the square root of 36. Well, we know the square root of 36, that's 6. The square root of x squared is the same as the square root of x times the square root of x, which is the same as the square root of x times x. One x goes out, one x goes away. The square root of x times x is just x. Hopefully you see a pattern here. Let's fill in the other ones here. So the square root of 19 squared is the same as the square root of 19 times the square root of 19. I could write it like that. We know when we take a square root, one factor comes out of the radical, one factor is dropped. This would just be 19. I think you maybe are starting to see the pattern here, right? And the square root of 3 squared is the same as the square root of 3 times 3. One 3 comes out, one 3 goes away. That's just going to be 3. So the square and the square root cancel one another because they're inverse operations. So that makes it really easy to figure out the square of a radical. You're just going to drop the radical. So that's pretty easy. And okay, so Pythagorean theorem, here's another visual example of that. All right, so here we have 3 sides of a right triangle, and notice that the areas of those 2 squares whose sides are a leg in the triangle are equal to the area of the square whose side is the hypotenuse of the triangle, right? Because 9 plus 16 would give us 25. And that's exactly how Pythagoras showed that it was true all of the time for all of our right triangles. We're going to do one problem, and then I'm going to break this podcast, and then my 2 classes will be caught up. All right, so we want to find the hypotenuse of our right triangle, and this one is in your notes, right? And so you can add the work along next to this problem. All right, so our first step, we want to fill in Pythagorean theorem here. Remember, that is hypotenuse squared equals leg squared plus leg squared. This is moving so very slowly. There we go. Hypotenuse squared, oops, I don't want to move that. Hypotenuse squared equals leg squared plus leg squared. Our hypotenuse is x, and the square 6. 8 squared is 636. When you add that together, that's 100. And we know that the square root of 100, there we go, is 10. Right? So x there is just 10. Right? So add this one to your notes. Feel free to pause this tape because I'm going to end this podcast and start in with the next problem. All right, so put this in your notes, and then I'll see you in the next podcast. Bye for now.